Okay. Thank you very much, Phil. We'll move to, thank you. We'll move to the last speaker of this session, Professor Matt Collins. He has a joint Met Office chair position in climate change with the College of Engineering, Mathematics, and Physical Science at Exeter University. And his research interests are in physical aspects of climate change. Matt was a CLA for the chapter on extreme events and risks. So thank you, Matt.
Thank you very much. We talked a bit this morning about the impacts of extremes and the role of extremes over land. So I'm going to talk about a few extreme things in the ocean. Same caveat as Mike. I was an author of the chapter on extremes, but there's some other stuff in here from chapter 5, which is the sea level chapter, which I will also cover. Okay, so I'm going to talk through a couple of diagrams, a couple of the sea level diagrams from the summary for policymakers. So this is the part of the process where you get locked in a room, something like this, for several days and nights to agree sentence by sentence. So it kind of throws up some interesting aspects, probably some interesting psychological aspects, but also some interesting ways of which some of these phrases come out. So this is the figure SPM1. This is the kind of summary of all the physical changes, physical and chemical changes in the system, both from a historical point of view, observations and models, and future projections. Just an aside here, there's the 1.5 report made a good play on of dissecting the impacts of climate change under different levels of warming. Now, on this report, we've tended to go back to these RCPs. Now, why have we done that? The reason is because the ocean is kind of an integrator of the pathway of the radiative forcing. So it's not just the level of warming that matters, but it's how you got there also matters. And in fact, much of the sea level rise we're going to see in the next few decades is already kind of baked into the system from our historical emissions. What this figure shows is the kind of main primary drivers of sea level rise in the past and going into the future. So that's from the Greenland ice sheet, the Antarctic ice sheet, the glaciers over land, and this, which is so all of these on the y-axis you see meters, so about going up to about 30 centimeters. All these kind of things contribute kind of roughly equivalently. The part of the warming that is kind of baked in is this ocean heat content change in your policymaker favorite units of zettajoules, 10 to the 21 joules. Try and explain that, even to a scientist. It's very difficult, I think. And what we had originally, before we went into the approval plenary on the bottom, was the sea level rise up to 2100, because that's where we have the most confidence in the models. But the policymakers very much wanted us to push that out to 2300. So you see this kind of graph, which shows sea level rise going off the scale. It's hatched, indicating there's some significant scientific uncertainties here. But we're talking, under the RCP 8.5 scenario of 3 to 4 meters of sea level rise in the next, 250, 300 years. I'm not quite sure. We're down in the basement. I'm not quite sure what level we're at. We might even be below sea level, I guess. But, I mean, that is a significant perturbation, as you'd imagine, to the system. What I want to talk about is the extreme events. So jumping to figure SPM4, this is an assessment of extremes in sea level. So now, the previous figure sort of indicates that sea level rise is very smooth, but in fact it's not. And we know that, from our day-to-day experiences. There are variations because of tides, because of storm surges, large-scale shifts in the atmospheric pressure, etc., etc. So there is there is variability in sea level, and one way of characterizing that is in terms of what is called here the historical Centennial events. So these are kind of maxima in sea level events, so high sea levels, which might occur maybe once per century. So if we imagine that there's a historic Centennial event, a sea level rise event that happens once per century, with the average sea level going up, we expect to see that happen more frequently. So the question that this figure addresses is, at what point in the future does a 1 in 100 years event become an annual event? So something that we would, in the historical period, have only seen, once really in the historical record. At what point do we start seeing that every year? Now, this is shown as coloured dots. The way to calculate this, you have to have a good historical record of sea level variability in the past from a tide gauge or something. So we can't go around every part of the coastline of the world and calculate this factor because we don't have the observation. So that's why there are large parts of, for example, Africa completely miss out of this analysis. What the colour shows is the year in the future at which a Centennial event becomes an annual event. So we start seeing these very extreme events happening on a yearly basis. And you can see the blue colours are quite soon, in fact, kind of about now, because the historical baseline period is a bit further back. The red is mid-century, the yellow is kind of getting towards the end of the century, as is the white. So you can see that you see a lot of blue and red, particularly in the tropical regions of the world, indicating that these historically rare events are likely to become annual events by mid-century. Phil made the point, and Mike also made the point about choices, about whether we follow an RCP 2.6 like scenario or an RCP 8.5 like scenario. It's a bit difficult to make out, so what you can do is take a difference map between the RCP 8.5 and the RCP 2.6, and the light green blobs are, if you like, where the scenario makes a difference. So if we reduce our emissions, we can make a difference to the occurrence of these historically rare events. But the green, the darker green dots, actually where the scenario doesn't matter so much, indicating that we've already put into the system, so as I said, baked into the system, the sea level rise that we will realise in the coming few decades. And in fact, this is one of these rare things in climate change, which is kind of not scenario independent, but relatively insensitive to scenarios. Okay, so that was the sea level part. Oh, just to use some words to sort of follow up at some of the conclusions. So the global mean sea level is rising with acceleration in recent decades. This is one of these tricky phrases in the approval process. What does it mean to say that sea level rise is accelerating? Well, for the mathematically minded, it means both the first and the second derivative are positive, which is this bit of LaTeX here. It shows the beauty of mathematics. So you can just explain a concept like that in many fewer characters. And about the different factors, the ice sheets and the mountain glaciers and the heat content changes are kind of all roughly the same magnitude. I mentioned the extreme sea level events that are historically rare are projected to become once per year events by mid-century. And we've actually seen for these, in comparison to previous assessment reports, slightly higher upper tails of the distribution for RCP 8.5 because of the inclusion of information about the Antarctic contribution, and in particular the Antarctic ice sheet contribution to sea level rise. So that's a new piece of science. Some more extreme events. One thing that we focused quite a lot on in the chapter 6 was this concept of a marine heat wave. So what is that? It's a period of sea surface temperatures in the ocean which are warmer, much warmer than average for a kind of relatively long period of time. Could be a few weeks, could even be months. And there have been a number of these marine heatwave events historically documented. Some of them have names like the North Pacific blob, which happened in it kind of coincided about the same time as the big El Nino in 2015, 16, or sort of slightly before it. These have considerable impacts, and Phil mentioned the impacts on coral systems. So the purple dots on the graph on the right-hand side are where there have been severe coral bleaching events that we've already seen, we've already observed in the world, and they are on the increase. And the thing I don't show in this figure is the future increase. This is an aspect of climate change that we can be pretty certain about, actually, because as the global mean temperature rises, the frequency of these marine heat waves will increase quite significantly under the unmitigated RCP 8.5 scenario. They also have impacts over land as well, because the ocean temperatures are important for determining weather patterns, in particular in the tropics. We also collected together a whole. This is one of the beauties of doing these assessments. You can really get into the literature and collect, see the number of studies which have looked at using this new technique of what is called event attribution. It's basically saying that if you look at a historical event, you ask the question, how much more severe has this historical event got because of anthropogenic climate change? So you can say, if this had happened 100 years ago, and if it happened now, what's the difference in the intensities? And we found a whole load of studies. We have a big table, a whole load of studies which have looked at this for things like cyclones and tropical cyclones, extreme rainfall events associated with those cyclones, the marine heat waves that I've already mentioned, some flooding events associated with the ocean, not flooding events associated with rainfall necessarily, droughts, etc., etc. So there's the body of literature that's come along even since the AR5 using this event attribution technique shows the impact of climate change on these extreme events. And finally, just wanted to show this because it's a sort of pet topic of my own. Perhaps without explaining this complicated diagram, but this is all about El Nino events, which happen in the Pacific, as clearly illustrated in the maps that people have shown. So, although the Pacific is a long way away, this El Nino event is kind of like a marine heat wave, which encompasses the whole of that side of the Earth, if you like, and disrupts weather systems around the tropics and even in mid-latitudes. One kind of seemingly relatively robust result that we've seen from the climate models in terms of future changes is an increase in the frequency of these very extreme El Nino events. And we've had 3 of these extreme El Nino events in the historical record, 82, 83, 97, 98, and most recently 2015, 2016. So these have large impacts on weather and on societies and on fisheries and on many aspects of life on the planet. And this is actually another one of these phenomena which is relatively insensitive to the scenario. So we see similar changes in the RCP 2.6 in comparison to the RCP 8.5. So there's some sense that we're committed to seeing these things happening in the future, with the caveat that this is a model projection, so we have to make sure that we've evaluated the models correctly. So just to finish on some words, leave some time for some questions. So on the marine heat waves, so more than 80% of the marine heat waves that occurred between 2006 and 2015 have been influenced by man-made climate change. That's one of these kind of event attribution statements. And further projected to increase in frequency, duration, and spatial extent. So the frequency, you can calculate from the models the frequency of these events, and we get up to from something like 20 times under RCP 2.6 to 50 times pre-industrial levels of marine heat waves and all the associated impacts on these, what I've been told are called non-mobile ecosystems, so things like corals. In terms of the cyclones and the sort of atmospheric phenomena, that climate change has increased the precipitations and the winds and the extreme sea level heights associated with many of these tropical cyclones. And there's perhaps some emerging evidence that we're seeing more of the category 4 and 5 cyclones. Those are projected to increase in the future in terms of the intensity, but we're less certain about changes in frequency and very much uncertain about frequency of landfalling cyclones and hurricanes, etc., etc. So that's still something where the models are challenged because of their resolution. And finally, this extreme El Nino and La Nina events are projected to increase in frequency in the 21st century, under both scenarios actually, and that could have quite large impacts which we haven't quite properly assessed yet because we didn't have the literature. And I think I'll take some questions there, but I'll leave you with this is the survivors photo showing a small number of authors who made it through the final night to do the approval. Thank you.
Thank you, Matt. Any questions? There is one in the back, yeah.
Yes, hello. I'm Geraldine Satrebusson from Imperial College London. So you said we have increased evidence now of attribution of extreme weather events. And historically, that's been one of the challenges in communicating climate change, that is quite hard whenever something happens to connect it. So is there some kind of like updated guidelines that the IPCC has thought about to improve this? And now that we have more evidence that scientists can be more certain about making these links?
Well, it's not really an IPCC thing, but certainly this kind of science of event attribution is becoming operationalized within organizations like the Met Office. So the way this is done now, it's kind of interesting from a scientific point of view, because many of these studies have been put together a week or 2 weeks after a particular climate event. So fast, rapid publication. At some point, you don't need to go through that publication and peer review. It becomes a kind of scientific service, an operational service. So I think that there are certainly plans internationally for this kind of thing to happen on a more regular basis. It's harder for some aspects of climate. So for the rainfall part of tropical cyclones, it's relatively easy to do. For the winds and the sea level rise component, it's much harder.
Could you say a bit more about the reduction of ice cover in the Arctic, and particularly how much is baked in, and also what's said in the report about the possibility of very kind of rapid changes? To what extent is that process? Could we predict unpredictability in that process, and also the albedo effect? Could you say a bit about that?
Yeah. So I mean, the from the sea ice point of view in the Arctic, so for the summer sea ice, part of that is driven by ocean warming, which again is one of these things because the ocean's integrated all the energy imbalance in the system. It's continuing to warm up. Part of it is, of course, due to this ice albedo feedback that you just mentioned. So there are multiple processes at play here. Whether if we stopped emitting completely today, we would recover some sea ice. I'm not sure I know the answer to that question. I think there would still be some decline, but maybe the sea ice albedo effect might help us actually the other way. I'm not sure I completely have an answer to that, but there are multiple competing feedbacks.
There's a question here.
Question about the ocean from a land
Oh, dear.
hydrologist.
Sorry, it was going to be about the atmosphere.
Okay.
Which should be all right with. Similar, along the lines of the impacts of reduction of sea ice, do you say anything about the implications to the jet stream and the the
winter storms. Yeah.
the winter storms and the potential for locking in storm tracks.
Yeah, I think we said there are a number of studies on this, but they are not conclusive, or some suitably vague IPCC scientific language. So there are large uncertainties, or there's low certainty, or something like that. Because I think there's been a lot of there have been a lot of studies in this area. Some are more believable than others. Some have been hyped up quite a lot by the media, and I think we're still kind of working out quite how that can work.
Matt, you mentioned acceleration in sea level rise, and in the report there are some pretty frightening numbers of increasing sea level rise in the centimeters per year in 200 years' time or so. Can you elaborate a little bit on why that is, and are there a tipping point in Greenland and Antarctica sheet that have been?
Yes, it's not really my area, but there is this marine ice shelf instability. Am I getting that right? Ice sheets instability? Okay. I'm doing a project on ice shelves, so I should know something about it. So the idea that you can have very rapid destabilization of the ice sheets, and then they sort of essentially kind of slide off into the ocean. I think we reined back from making a very definitive statement about that. I think we felt that the science was still pretty uncertain. There's a couple of papers, but a couple of other papers which have contradicted. So this is, again, IPCC has to kind of reach a consensus. It's not about sensationalizing things. So just because something isn't in a headline statement doesn't mean that we didn't think about it. It's just that we thought that maybe there wasn't enough scientific evidence to make a definitive statement at this point.
Okay. Maybe one last question here.
Thank you. Just a question about if we're able to reduce carbon dioxide created by man. To what extent will the ocean bring out carbon dioxide which has been absorbed as to confound the issue further to some extent?
Over to Phil, I think. Give him the microphone. Sorry, Phil. You can give a more informed answer than I can.
It does depend on the dynamics of the system, but one can't just equate removal of carbon dioxide compared to the amount in the atmosphere. It has to be compared with what one puts in. So you've got to take out the equivalence of what you put in. It's that if you actually lower the carbon dioxide in the atmosphere, it will come out of the ocean. So that there is that. I believe that's the effect that you're referring to. But it does have to be done on a pretty massive scale. But it is quite easy to make the wrong calculations unless you understand the dynamics of it.
Okay, thank you very much, Matt. We